Hello, my name is Chance, and for my senior project, I chose to do a heat exchanger to use with an Omax water jet cutting machine. Reasoning for this project was the water in the tank can start to get really hot when the machine's being used for extended lengths of time, such as 12 or 14 hours cutting times in consecutive days. So when the water starts getting hot, it makes the not only the room uncomfortable, but it can cause warping in parts, more warping than what's already the case, and then it also makes it difficult for the user to grab parts off the table, and mainly it starts to heat up the room that it's in. So the goal of this was to design a device that could get some of the heat out of this water. Um, I've seen some of the hottest I've seen the water get in the tank is up to 130. It doesn't usually get that high unless it's really being used consistently and not being shut off very much. But this is the water jet here. Its tank size is 2,000 gallons, about. That's about how much water's in that tank. The pressure at the nozzle, which most times it's a high pressure setting, for cutting stainless and things like that, and it's 55 KSI. This water jet is located at the place I currently work, and they design and manufacture food processing equipment. So it's mainly just cutting stainless steel, so it requires the high pressure setting. So my first step in approaching this project was to analyze how much heat or energy is being transferred from the jet into the tank. Um, and that first analysis can be seen here. How I did this is I used a thermocouple actually and just touched it on the jet. Well, actually, I only zip tied it on there, but while it was being used, the average temperature it was after had been running for a few minutes, it was about 97 degrees, 90 to 97. So assuming that that's the temp of the water leaving the jet, um, I used that temperature and neglected any other heat transfer to the air and assumed that all heat energy from the jet was going into the tank water. And I came up with the number of 19 kilowatts uh, right here. So to test that number, I used it in a couple other analysis. If that was really the energy transfer rate from the jet to the tank water, it would take about 8.3 hours for the tank water starting at 68 degrees to reach 100 degrees, which that seems realistic to what I've seen. It does seem 100 degrees in 8 hours. It probably wouldn't be quite 100, it'd probably be like 88 or 90. But that makes sense because I neglected all other heat transfer. I assumed all heat transferred from the jet to the tank. So after 12 hours, it would be 115 degrees. So this number to use, 19 kilowatts, I just went with 20 kilowatts to base all my other analysis off of, such as I'm already given a mass flow rate, or a flow rate for the pump, so using that variable and what the heat transfer rate needs to be, I could figure things out such as surface area, volume flow rate for air, and things like that. So this project requirements I set as it needs to keep 2,000 gallons of water below 100 degrees, needs to run 12 hours a day at minimum. Ideally, this will work best when it's running overnight when the jet's not being used, so it can actually pull heat out of the water while heat's not being put into the water. If it's being used while it's running, hopefully it would just keep it cooler. This would needs to be able to maintain cooling in ambient temperatures of 40 to 100 degrees, so it needs to be able to be used when it's that temperature outside. The flow rate is a 3 to 5 gallon per minute. The entire unit must not be larger than 48 cubic feet, because this would be deemed as, if it was any larger than that, it really wouldn't be movable. And the reason that it needs to be movable is it can be pushed outside to let all the heat outside, but also during the winter it can also be put in other parts of the building, and the water can be pumped and heat can be released in another room, so it's keeping the manufacturing floor at a cooler temperature, but heat can be put in other areas that may not have as much heat. But there's many more analysis that can be seen here by clicking all green sheets. So the start of construction, I made the copper, or all the passes from the pipe were all done out of copper, 3/8 type M copper, so it actually has an inner diameter of 0.44, not 3/8, but it's a 1/2 inch OD. The stand's out of aluminum, and the fins are out of aluminum, which it can be seen right here. This is the mount I was actually cutting on the water jet. Well, it's under the water, but I cut it on the water jet just so the holes would all be in a precise location so I could match all my fins to it. And there, what's being turned on the lathe is a stainless rod that connect the two mounts together, and the ends would get drilled and tapped. I didn't actually end up using the stainless rod because I ended up doing everything else out of aluminum, so I just did this same thing but with a aluminum rod. Here are all the fins. I wanted to cut all the fins on the water jet because then they'd be all exactly the same, but I ended up, there's 116 fins total, and they're not all in that picture, but there's about stacks of 10 to 12 there, and I had a template, and I had a tiny drill bit. It was like a 3/64 drill bit for a pilot, and I drilled each hole. There was actually 3,712 holes. Then I went through and drilled them at a larger size. This helped reduce time when they're all stacked together, and also kept all the holes together, so assembly would be a little bit easier. Assembly took quite a while because each fin had to be pressed on just because it was such a snug fit. I made a little wooden, I guess you'd call it a jig, that slid over the pipes, and that way I could use a mallet or a hammer to press the fins on equally. So that took a while. Once it was fully assembled, it has a fan on the back and just runs off a 110, as well as the pump also. So for testing wise, my main test that I needed to do was test the heat transfer rate. And my goal was to have 20 kilowatts. The test I did, it was in ambient temperatures of 68 degrees, and the heat transfer rate was actually only 18.7 kilowatts. It should have been 25 in those conditions, so it did not meet the requirement of having a 20 kilowatt heat transfer rate. There are some things that can be done, I think, that could easily get it to above 20. But in this case, its max rating during that test was 18.7. It did keep the water, however, under 100 degrees after running for an hour, and then that's when it started to flatten out. There's also a test that was done, I did a pressure test and a stand deflection test to test if the stand could handle all the weight of the water and the rest of the unit. For budget, it was about $1,300. I came in a little under that, at around $1,200. I didn't actually have to spend that. Much of the materials I already had in possession, and a lot of them were given to me. Schedule, I initially estimated 180 hours. It ended up coming in at about 160, so I was actually 20 hours under what I thought it would take. And On the last page here, I have my contact information, and my full report can be seen on the front page here. So thank you for watching, and thank you.